So any questions about last lecture's material? Any questions about the homework? Actually, the first thing I should probably do is show you the schedule. So this has changed a little bit. How do I get rid of this? So, the stage 5 for project 1 is mainly going to be scheduled on the 24th and 26th. Those of you who requested wanting to demo your project earlier will be able to do it on the 19th. The stage 2 of project 2 will be also in the week of the 24th. So that is also going to be a little delayed. So that way you guys have more time to work on both project 1 and project 2. Okay, so that's to take a look at the deadlines, and if something isn't clear, let us know. The other thing to note is that there's no class on the 19th. So I'll be out of town for a conference, so there's no class on that day. Okay? All right. And by the 1st of May, you should be done with the course. There's nothing else beyond that. Okay, so we were talking about extensible hashing. So the basic idea behind extensible hashing was this notion of having buckets that repeatedly double whenever there's a need for it, while the data blocks are shared across various buckets. So you could have a scenario where you have multiple buckets pointing to the same block, right? You have multiple buckets pointing to the same block, so you will only initialize new blocks when you absolutely need to, so that was nice. The second thing that was nice was that there was no need for any overflow blocks. Okay, so there was no need for any overflow blocks. Both of these things allowed us to circumvent the issues in the original vanilla hashing implementation, which had overflow blocks and would in many cases require a lot of lookups in order to find the records that you care about. At the same time, extensible hashing wasn't great. And why was that not great? Well, it was not great because the extensions are costly and disruptive. When you're doubling the number of buckets, that's not a cheap operation. And because of that, at periodic intervals, whenever you needed to double, that would be a disruption. You would have to wait until the doubling was finished. And this could take quite a long time. Okay, so that was the first issue. The second issue is that after you do this doubling, this new bucket table may not fit in memory. Okay, and this is also not a desirable solution, because if the bucket table does not fit in memory, then you're going to have to spill to disk, and then retrieving stuff from disk isn't cheap. The third issue was that often this mechanism would end up allocating space in the bucket table even though it was not actually necessary. So let's say you had 3 records that intersected in the first 20 bits. You would end up having a bucket table that was order of 2 to the 20 even though you have only 3 records. Okay? So this issue led to the fact that basically you were initializing more buckets than you absolutely needed. Okay, so you were having more buckets than the number of records. That is not desirable. Okay, so these are the issues with extensible hashing. So now let's move to linear hashing. Any questions about extensible hashing? Any questions about the issues with extensible hashing so far? Okay, so let's get into linear hashing. So linear hashing, like the name suggests, adds one bucket at a time. It doesn't add a collection of buckets like in extensible hashing. Extensible hashing always doubles. Linear hashing doesn't do that. It adds one bucket at a time. And one issue with not doubling every time is that n, the total number of buckets, is no longer a power of 2. But this doesn't affect us that much, because we can think about n as between 2 powers of 2, and that allows us to sort of smoothly increase the size of the bucket table as you need to, and I'll show you how. And the other thing about linear hashing that is a little different from extensible hashing is that it's going to use the last I bits to represent the bucket or membership in a block as opposed to the first I bits. Okay, so this is a little confusing, but so something to keep in mind. So this is using the last I bits, but again, once I go through the example, it'll become clear why using the last I bits as opposed to the first I bits actually makes sense in this case. Now, the way it deals with this, the fact that n is not a power of 2 is that if the last I bits represents a number that is greater than or equal to n, then we will change the most significant bit of those I bits from 1 to 0 in order to get a number less than n. Okay, so everything that is greater than or equal to n is rounded down, if you will, to a number that is less than n. Everything that's less than n will stay as is. Okay, let me keep going, and then hopefully with an example things will become clear. The second idea here is that we will allow overflow blocks. We are okay with having a few overflow blocks as long as it doesn't significantly degrade performance. So it's not expensive to overflow like in extensible hashing. So in some sense we are being a little more tolerant, and that little bit of tolerance will actually help us with the worst case scenarios that we will encounter. Okay, so let's say you have n is equal to 3, so your n value is 3. This is less than 2 to the power of 2, which is 4. The number of bits that you care about is 2 bits, so I is equal to 2, and you have 3 buckets so far, so 0, 0, 0, 1, and 1, 0. These are the 3 buckets, so therefore n is equal to 3. Now, in this case, the last 2, you're reading from the right as opposed to the left, so it's the last 2 bits that are relevant because I is equal to 2. So since the last 2 bits are relevant in this record, the last 2 bits of the hash value is 0, 0. Therefore, it is hashed inside this bucket corresponding to 0, 0. Similarly, this one has last 2 values as 0, 0, so it's hashed inside this block. And this one, I'll do the easy cases first. This one is 1, 0, so it's hashed within this block. On the other hand, this one is actually 1, 1, not 0, 1. But turns out we don't have a bucket for 1, 1 yet. So we are going to do a bit flip for this bit and transform it into 0, 1 and then hash under 0, 1. Okay? Once again, another way to think about this is you have 1, 1. 1, 1 is equal to 3, right, in binary. So 1, 1 in binary is equal to 3 in integers. Therefore, since 3 is equal to n, we are going to have to flip the most significant bit. So you'll flip the most significant bit, which is 1, and you'll get 0, 1. So you're going to hash it based on 0, 1. Okay? Questions about this? Yeah.
But the data stored remains 0, 1, 1, 1, right?
Yeah, the data stored remains 0, 1, 1, 1. This is just how it's hashed. So you're not transforming the data in any way. This is just how it's hashed. Any other questions? Okay. So, so we now know how to interpret a linear hash table. Let's think about how to insert stuff. So let's say I have a new record with hash value 1, 0, 0, 0. Now my I is equal to 2, right? So I'm interested in the last 2 bits of this hash value. The last 2 bits are 0, 0. 0, 0 in integers is simply 0, right? And because it's 0, it's less than n, right? N is 3 in this case, so it's less than n. Therefore, all I need to do is to take this 0, 0 and hash it as is. I look up 0, 0, and then I will want to place it in this block. Okay, so that's what I would like to do. Now, there's no space in this particular block, but linear hashing actually allows me to use overflow blocks. So I can certainly go ahead and add an overflow block. So this is a pointer to an overflow block, and add the new record within that overflow block. However, I can't just keep adding records to overflow blocks without worrying about it. There is a constraint that I have to meet. The constraint that I have to meet is that I will allow records to be added to my hash table and also initialize overflow blocks up until the point when the average number of records per bucket exceeds 80% of the total number of records per block. Okay, so let's try to digest that for a second. So the average number of records, so let's say I'm in this setting, the average number of records per block. Let's first count the total number of records. So total number of records is 1, 2, 3, 4, 5. Right? So I have total number of records is 5. And the number of buckets that I have is actually 3. Right? So the number of buckets that I have is 3. And the total number of records that are allowed in each block is 2. So the fill factor in this case is actually 5 over 6, which is roughly 80 something, 83% or something. Okay, so this is the fill factor. So once again, the fill factor is the total number of records divided by the number of buckets times the capacity of each block. The number of buckets is 3, the capacity of each block is 2. So this is roughly a fill factor which indicates how filled up is my hash table. Okay, so 83% basically indicates that this is pretty filled up. If it was closer to 0, this would mean that it was relatively less filled up. Now, as the fill factor increases, I want to seamlessly increase the size of my hash table. So I want to increase the number of buckets. So in this particular case, I might say that I want to extend n to n plus 1 when the average number of records per bucket exceeds 80% of the total number of records per block. So what that means is, let's say n is a total number of records, b is the number of buckets, and r is the number of records per block. As soon as this exceeds 80%, I want to increase n to n plus 1. Okay, so I want to, actually let me use a different symbol because this would get confusing. Let the number of records be m. So if I have m divided by b times r is greater than 80%, then I'm going to increase n to n plus 1. What does increasing n to n plus 1 end up doing? M will end up being the same, r will end up being the same, r is a constant, this is just the number of records per block, while b will increase, right? The number of buckets will increase by 1. Okay, so the fill factor will decrease as soon as you increase the buckets. If you add another bucket, the fill factor will reduce. Any questions about this? Okay, so as I'm adding stuff, I need to make sure that the average number of records per bucket is does not exceed some threshold that is dependent on the total number of records per block. So in some sense, this is the average number of records per bucket that I'm trying to constrain and keep it minimum or keep it small. Up until that point, if I have not met the threshold, then I can certainly use overflow blocks. And certainly use overflow blocks. Overflow blocks are not a problem as long as this threshold is met. This threshold is essentially a type of fill or capacity factor. So the overall goal is to ensure that the fill factor for buckets is kept small, such that we prefer overflow blocks up until a certain point. When we have filled up stuff too much, if we filled up stuff too much, we'll increase the number of buckets. Okay? So I think that might be it. Okay, so I have one more example. So let's say I have I've decided at this point that I want to move from n is equal to 3 to n is equal to 4. This example shows me how I'm going to do that. So what I would do is I would first add another entry to the bottom. I would change and I would associate that with 1, 1. I would change n is equal to 3 to n is equal to 4. Next, I need to possibly create a new block corresponding to 1, 1. Okay. Now, in order to figure out which records belong to this new block, all that I need to do is to look at 1, 1, take the most significant bit, which is 1, change that to a 0. So I'm going to go back to this particular entry, go to the records in that block, and steal all of the records which have 1, 1 at the end. Okay? So I'm going to take away this guy, I'm going to add it to 0, 1, 1, 1 at this block, because the last 2 bits are 1, so it has to be in this block. If, on the other hand, this block also had something like 0, 0, 0, 1, that will stay in that current block. Okay, that record will stay in that block. The only thing that I'm going to move to this new block is those that have the last 2 digits 1, 1. The only place where I will find records with the last 2 digits 1, 1 are those that are currently in the block corresponding to 0, 1. Okay? The current block 0, 1 will contain all of those records that I need to find which have the last 2 bits as 1, 1. Okay, so in this case, all I'm going to do is to steal 0, 1, 1, 1, place it in the block corresponding to 1, 1, and I'm done. Okay? All right, so the next step, let's say my threshold has dictated that I want to move from n is equal to 4 to n is equal to 5. Okay, so I'm moving from n is equal to 4 to n is equal to 5. Okay, so what might I do in this case? Any thoughts? So the first thing that I need to do is to add a new bucket. What would that bucket be associated with? Where would that bucket be added? Any suggestions? Yep.
You'd have to change I equals to 3.
Sure, I will be changed to 3. That's an important step. What about changing the buckets? Yep.
I think you'd have to add 0 in front of all the current ones, and the next bucket would be 1, 0, 0.
Absolutely. Right, so what you would end up doing is essentially thinking about adding a 0 at the start of all of these ones, but really you don't need to do that because the meaning of those numbers don't change. In binary, when you convert it to an integer, it's still going to mean the same, so you don't really need to add the 0. All you need to do is to add a new bucket with 1, 0, 0 at the end of it. Okay? So now you've created a new bucket. What do you have to do next? Yep. Yep. So I may want to create a new block for that bucket. Where would I bring records from for that block? Correct. Right. So the only block that I need to consult to populate this block is this one, because it contains. So since when I was in n is equal to 4 or n is equal to 3 or any of those numbers, I was always rounding down anything with 1, 0, 0 to 0, 0. Right? Since I was rounding down everything to 0, 0, all the records with 1, 0, 0, I'm going to find within the block corresponding to 0, 0. Okay, so I need to look at this particular block in order to find all the records that I would need to fill up 1, 0, 0. And in this case, both this one and this one match that condition. So I'm going to erase it from 0, 0, 0, and I'm going to add it to this one. Okay, so it's 0, 1, 0, 0, and 1, 1, 0, 0. Again, the parentheses are just for your convenience to indicate which bits are not important for that block. It's not actually something that is stored, but it's just something for convenience. It's not something that is something that impacts how the hash table looks like or how you operate on it. Okay, so if I were to use a parenthesis here, I would use one around 0 in this case and around 1 in this case, because now I care about 1, 0, 0 and I'm associating that with the block as opposed to just 0, 0. Okay, so it would be 0, 1, 0, 0 and 1, 1, 0, 0. Again, this is just for convenience. This is not something that the implementation needs or cares about. I think that's it. Any questions about hashing? Any questions about linear hashing? Comparisons between linear hashing and extensible hashing? Last chance before I move to the next topic. All good? Okay. Right. Let's see. Look. All right then. So the next topic that we're going to be talking about is query processing. So it's important to think about where we are within the database and associate that with the topics that we've covered so far. So we've spent a lot of time on the querying layer, which is in some sense what the user sees. So we talked about relational algebra, we talked about SQL. This is how a user of a database would interact with the database. We've also spent a little bit of time on the views and the triggers layer. This is not what the user typically sees. This is what the database administrator would add. So the database administrator would add views for convenience or allowing users to only look at portions of the data, or they may add triggers to ensure that certain constraints are met during normal database operation. We spent a little bit of time over the last couple of lectures on indexing. So indexing in some sense is a start of peeking under the covers. Okay, this is impacted by the administrator. So an administrator can say build an index on something, but really how the index is built is under the covers. This is something that is done by the database system. Query processing, which is another thing that we're going to cover right now, is also under the covers. In fact, it's even more under the covers than indexing. This is deep in system internals. This is how, in some sense, a SQL query or a relational algebra expression is evaluated by the database. So this is deep in database internals land. This is really the bread and butter of database system internal developers. So these are people who are building database systems from scratch. So this is the kind of considerations that they would think about. What I'm going to end up doing in the next few lectures is to give you some kind of a bird's eye view to this topic. This is not going to be sort of comprehensive. This is not going to be super detailed. This is because it's a very, very complex topic that is with many considerations that we are not going to be able to cover in an undergraduate course. So if you want to learn more about this, I would encourage that you take Advanced Database Systems 511 or some of the other seminar courses. Okay, so these are this is what people do research on. So if you're a database researcher, you end up doing research on topics like the one that I'm talking about. Okay, so the next few lectures is going to cover two things. The first is, given an execution plan, how do you process that execution plan, and also how do I pick a good execution plan. An execution plan is simply a procedure to execute a query and give you the results for that query. I don't know why I did this, but so let's say you have a select from where clause. So it's a simple query. The first thing that you end up doing is you transform that query into what is known as a logical query plan. A logical query plan you can think of as a relational algebra expression. So in this case, you can think of one possible logical query plan would be to take all of these relations R1 to Rk that are listed in the from clause, do a cross product, then do a selection operation after that on condition C, which is from the where clause, and then do a projection onto the attributes A1 through AN. Okay, so that actually tells you a logical query plan. It is declaring a sequence of operations. So the next step that is done by the database system is to transform this logical query plan into actually how it's done on the data. So this is a physical query plan. A physical query plan needs to be very aware of how the data is represented on disk, how you can actually operate on it, so it needs to be a lot more closer to the data and less high level. Okay, so today we are going to be talking about the operations that are part of this physical query plan. What are the costs and trade-offs, spend a lot of time trying to understand what are the benefits of each operator implementation, and what are the costs and the memory requirements for each of them. Okay, so once again, the trade-off between logical and physical operators is as follows. So the logical operators are like relational algebra operators. They specify what is happening, what the operators actually do. So it specifies that you are doing a union or a selection or a projection and so on, while the physical operators specify how it's actually done. So for instance, if you're doing a join, there are many implementations of a join. You could do a nested loops join, a sort merge join, or a hash join, or an index join. All of these are possible implementations of join. So physical operators are particular implementations of relational algebra operators. Physical operators also pertain to some non-relational algebra operations, such as scanning the data. So if you're just scanning the data, there's a physical operator for that as well. That doesn't really correspond to a relational algebra expression or an operator. Okay, so let's start with getting all of the tuples from a relation. So scanning a table. So you want to either read all of the contents of a relation R, or you want to find all of the tuples that satisfy a certain condition from that relation. So it's partial contents. One option is to do table scan. So table scan basically says the system knows that a relation is stored across a certain collection of blocks on disk. These blocks are known to the system, and then you simply retrieve these blocks one by one. That allows you to scan through the relation. Okay, not super surprising. You're simply bringing one block at a time, scanning through it. This is the simplest approach of reading through a table. Okay, this is a table scan. The second approach is using an index. So we saw two examples of indices multiple examples of indices in the earlier today and the previous lecture. So index will allow you to get the blocks of a relation or the tuples of a relation in a certain order. So if you have an index to find the blocks, you can scan the index and grab the relevant blocks. This is especially useful if you want to subselect a set of blocks that satisfy certain conditions. Okay, so if you want all of the tuples of students who are in the CS major as opposed to the other majors, you can use an index to find all of those tuples. This will require looking at much fewer blocks than if you were to do a table scan. Okay, so this is the second approach, which is using an index. A third approach is to sort the tuples as you're scanning them. Okay, so you may wonder, why would I want to do extra work? Why would I want to sort the tuples as I'm scanning them? There are many reasons why I might want to do that. The first reason would be to use a clause which is called order by that enforces that the tuples that are returned by a query result are ordered. Also, in some cases, some relational algebra operations are implemented using sort. So things like union and intersection require a sort before performing the operation. Remember that union and intersection default to set semantics, while the other operations default to bag semantics. Okay, so union and intersection require you to to perform some kind of sorting, so it's useful to do that before the union operation is done. Lastly, some other operations may actually be cheaper. So if you wanted to do a group by, if you wanted to do a join, these operations may actually be cheaper if you are sorting the relation as you're scanning it. So how would you want to do this? What are the various mechanisms that you can use in order to sort a relation as you're scanning it? The first approach is via using an index. If you have an index on the attribute that you're using to sort, then you're in great shape because you can retrieve the blocks in sorted order using the index and you're done. You don't need to do anything else. The second approach is if the relation fits in main memory, then again you're in very good shape because you can bring the blocks of the relation into main memory, then do the sort within main memory, and you're done. So you basically do table scan or index scan and then sort within memory. So of course if you're using an index scan on the attribute that you're doing a sort on, there's no point further sorting it. But if you're doing an index scan on a different attribute, you may still want to do a sort. Right? So if your index is on A and you want to sort on B, you might retrieve things in sorted A order, but you may then want to sort it in memory to be in sorted B order. Okay? All right. So the last approach would be to do something called as multi-way merge sort, which requires multiple passes on the data, and I'll get to that in a little bit. So even for the simple operation which is scanning, you have multiple alternatives, right? So you have the one alternative which is to just do a table scan, the other alternative which uses an index, the third alternative which is doing a sort, and within sort you have many alternatives again, right? You can either use an index, you can do sorting in memory, or you can do a multi-way merge sort. Okay, so there are lots of variations of physical operators, and that's what makes this topic a little challenging. Any questions so far? All good? Okay, so in order to pick between these implementations, so I have already 3 or more alternatives for scanning. Now, in order to be able to pick between them, I need to have a mechanism for associating costs to these operations. I need to have a mechanism for associating some form of benefit, some form of performance information for each of these operations. So, in order to pick between various physical operations, we need to estimate the cost of each of these physical operations. And estimating this cost is important in optimization, in picking a good physical query execution plan for your query, in picking what you actually end up doing in order to execute a query. In doing so, in estimating the cost, what we are going to assume is to simply compute the disk I/O requirements. Okay, the input-output to disk is all that we are going to be focusing on. We are not going to be focusing on the memory computation complexity, the computation requirements, because often the disk is the bottleneck. Okay, getting stuff to and from disk is what is a bottleneck, because disk is fairly slow. The databases are often large, so they don't all fit in main memory. So you have to store them on disk. Bringing stuff from disk is usually the most complex step. It's usually the most expensive step. So we're going to be focusing on the disk I/O cost. You can certainly add on memory requirements, computation costs as well, but that only makes the problem a lot more complicated. Okay, so we can make it more complicated if we like to, but for simplicity, we're going to be only focusing on the disk cost, so disk I/O cost. The second thing that we're going to be making a restriction on, so the first restriction is that we're focusing on the disk I/O. The second restriction is that we are not going to compute the cost of writing the result of an operation. We are only going to compute the cost of reading the arguments of the operator. Okay, so when you're done with computing the results of the operator, you're going to have to write the results onto disk once again. That operation is not something we are going to count the cost of, because that stays the same independent of which physical operator you end up using. Anything that you do before then, so any reading and writing that you do before then, we will count the cost of. Okay, so we do compute the cost of reading the arguments of the operator. We will count the cost of writing any intermediate reading or writing any intermediate results. But the cost of the final result is not something we are going to count. The cost of writing the final result is fixed. This doesn't change from operator implementation to operator implementation. This is not something we are going to count. Another reason why we don't count this is, in many cases, you don't actually write the result. You might simply show it to the user. You might give it to another operator. So you might scan a relation and then apply a selection condition after that. So you don't really write it back to disk. You might pass it along to the next operator. So this is another reason why we don't count the cost of writing the result of an operator. We will only count the cost of everything else up until that point. Okay, and once again, the granularity that we are going to be operating on is in these disk IOs. This is the operations that we are doing in moving data from and to disk. All right. So in order to reason about cost, we need certain parameters or statistics. So the first parameter that is important for us is the number of blocks that fit in main memory. Why is this important? If you have a very large number of blocks that can fit in main memory, if you have, let's say, a 1 terabyte main memory machine, then you're in great shape. A lot of databases can fit within that. So this is an important parameter. The second parameter that's important is the total number of blocks that are needed, absolutely needed to store R. So this is the best case number of blocks. So if you packed all of the tuples of R tightly into a small number of blocks, B of R would be the best case number of blocks. Okay, so let's say blue stuff in this figure refers to tuples. If you packed all of the tuples of a relation R tightly, in this case, it looks like it fits into 2. So this is the number of blocks that are required to store R in the best case scenario when you packed everything tightly. T of R, on the other hand, is the number of tuples in R. This is also the worst case number of blocks. What is the worst possible scenario? The worst possible scenario is your tuples are spread out across as many blocks as possible. So you have 1 tuple per block. So the total number of blocks is the total number of tuples. Okay, that's a worst case scenario for a relation. You can make it even worse by splitting tuples into, take a 1 tuple split into 2 blocks, but that doesn't happen. We never split a tuple across blocks. We fit tuples within blocks. Because we are fitting tuples within blocks, the worst case number of blocks is the number of tuples in R. The other quantity that I will mention now, but we won't focus on up until later in the class, most likely not today, but in the next class, is the number of distinct values. So V of R comma A is the number of distinct values of attribute A in relation R. Okay, and one way to relate the T of R quantity with the B of R quantity is simply T of R divided by the number of tuples that fit in a block is equal to B of R. Okay? Any questions about these cost parameters? Right, let's move on. So beyond the cost part, the other thing that's useful to think about when considering various operator implementations is how you envision operations happening between the database system and disk. Okay, the way to think about that is to have some kind of a mental model for what a database system looks like. So a database system in its most simplified implementation looks something like this. There's some kind of a controller which is doing the processing. There is a buffer space which is storing blocks temporarily. So this is a temporary computation or temporary storage space. And buffer, the buffer again, like we saw earlier, M is the number of blocks that fit in main memory. These M blocks will populate what is the buffer. Okay, the M blocks are the buffer. Okay, so the buffer is a temporary computation space. It is a space where you bring in data from disk. It's where it's going to sit. And if you're going to throw away stuff back into disk, it's where you're going to create those output blocks. Okay, so input blocks coming from disk are going to sit in this buffer. Output blocks, once you're done processing them, will go back from the buffer to disk. Okay, so the buffer space you can think of as temporary computation space. It's conceptually divided into these blocks, and there are M of these blocks. These represent your units for computation. Okay, so these are the units of computation. And then you have disk, and the blocks are laid out on disk. Okay, so there is you can think of a disk controller, which basically says, if the database system says bring me block I, the disk controller is going to go grab block I and then return it to the database system. The database system may choose to populate a certain buffer location with block I. Okay, is this clear? All right. So let's go back and revisit the operations, the physical implementations of scan, and then talk about how we can use these cost parameters to estimate their cost. To do so, for now, we're going to assume that the data is densely packed. So it's basically fitting into B of R blocks. So you just packed all of the tuples of the relation into B of R blocks. And let's see what happens, right? So the table scan cost is very simple. It's simply B of R. Why is it B of R? Well, I need to read the relation once, right? So I need to read the relation in once. There are B of R operations of bringing one block at a time of the relation into my buffer, and basically that has a cost of B of R. Remember once again that we are only counting the cost of everything up until the point where we are writing it out. So we are not counting the cost of writing out the results of this operator, only everything up until this point. The only operation that's happening up until this point is reading the relation into memory. Okay, and the cost of that is B of R. The cost of an index scan is B of R, which is the cost of bringing all of the blocks of relation R into memory, plus the blocks of the index. So you'll have to first bring the blocks of the index into memory, and then decide using the blocks of the index which blocks of the relation R you want to bring, and the order in which you should bring them. So this typically, the blocks of the index is typically not very large, and therefore this is typically order of B of R. So you may be thinking, why would I ever want to pick an index scan over a table scan? Well, the reason for that is that the index scan may allow you to sort the relation as you're scanning it. That might be beneficial. The index may also allow you to skip a large fraction of your relation as you're scanning it. Again, that might be helpful. Table scan, on the other hand, even if you want to apply a selection condition, you can't do anything much with it. You still have to pay a cost of B of R. Index scan, on the other hand, your cost may be substantially reduced if a few number of tuples satisfy your selection condition. Okay? Are you on board with this? Okay. So what about sort scan, right? So that was the third implementation that we talked about. So if I wanted to do sort scan, and let's say my first assumption is that the relation is small, and remember that I have M main memory blocks available for me to use. This is my buffer. Let me also make the assumption that B of R is less than or equal to M. So the relation is small enough that the number of blocks that I need to store R is less than or equal to M. So all that I need to do is to bring all of the blocks of my relation into memory and then apply my sorting operation within memory, and I'm done. Right? So I only need to read the relation once. So the cost of sort scanning, if the relation is really, really small, which is in particular it's smaller than m, then the cost of this is simply b of r once again. Okay, so it's pretty small. But if the relation isn't that small, then we need to do a multi-pass, multi-way merge sort. So let me describe the two-pass multi-way merge sort here. So once again, we have m main memory blocks available for us to use. So what I'm going to do is, let's say this is my sequence of blocks for the relation. And let's say my number of main memory blocks that I have, m, is equal to 3. So I can only accommodate 3 blocks at a time in memory. So what I'm going to do is to simply grab 3 blocks and then sort it and then write it down in sorted order. Okay, so I'm grabbing 3 blocks at a time, sorting, writing it out in sorted order. Grab once again 3 blocks, sort, and then write. And for convenience, let me just have 3 more here. Sort and write. Now what I have basically is the result in some sense is runs of length m on disk. So basically what I have is sorted sequences of blocks of length 3. Right? So I've taken blocks of length 3 or 3 blocks at a time, done a sort and then stored it on disk. So now I have 3 blocks, 3 sequences of 3 blocks such that these 3 blocks are all in sorted order individually, right? So this is a sorted sequence. Okay. The next step which I'm going to do is essentially to do a merge. So I'm going to merge m minus 1 of these runs at a time, construct the output, and then write to disk. So as it turns out, in this particular case, I don't have the space to execute this. So I'm going to simplify my example and then explain why it is why I wasn't able to do it in a second. So let me erase this. Let me just have 2 sorted lists for now, and I'll consider the more complicated case in a second. Okay, so let's say I just have 2 sorted lists. So I have, or rather, 2 group your b of r. Didn't want to do that. M is equal to 3, b of r is equal to 6. Okay, I'll get to b of r is equal to 9, which is what I was trying to do earlier later. So let's say b of r is equal to 6 and m is equal to 3. What I've done first is to take a group of 3 blocks at a time, sort it, write it out. So I've done that for this sequence and I've done it for this sequence. The next step is to merge m minus 1 of these runs at a time. So this is run 1 and this is run 2. Okay, so I'm going to have one of my 3 blocks in the buffer dedicated to run 1, one dedicated to run 2, and one dedicated to my output. Okay, so I'm going to grab the first block in sequence from run 1, the first block in sequence from run 2, perform a merge, much like a merge sort, and then write the results to the output, and then this output is written out to disk. Okay, so this is essentially like a merge sort. So essentially what you're ending up doing is you're partitioning your data into chunks. Each chunk is sorted, stored on disk, and then you're bringing up multiple chunks at a time and then merging them and then getting the output. So let me walk through an example here. before I get back to these constraints. Okay, so let's say I have m is equal to 3, each block holds 2 values. So I have these 6 blocks, so b of r is equal to 6. The first step is to sort the runs, so I will grab these 3 blocks, store it in memory, sort it, and then write it out to disk. So I have these 3 blocks that I've sorted, written out in this way. I have these 3 blocks that I've sorted, written out in this way. Okay, so now I have these 2 runs that are both stored on disk. Now I need to do a merge. So my merge is basically going to grab 1 block from run 1, 1 block from run 2, and then try to do a merge of these 2 and then store it in the output block. So what I'm going to end up doing here is to look at 1 and look at 0, pick the smaller of the 2 values, store it in the output, so that's going to be 0. So I've already done processing 0. Next I'm going to look at 1, look at 2, pick the smaller of those 2 values, store it in the output, so that's going to be 1. I'm done with 1. Okay, so I've filled out my output block, so I can go ahead and output 0, 1. Okay, so now I'm basically done with 1, I'm basically done with 0. I have 3 and 2 at the heads of those 2 blocks. I'm going to take 2, make it part of the output because 2 is smaller than 3. Now I'm done with this block, and I'm going to take 3 and place it here. I'm done with this block. Essentially, I can go ahead and output 2, 3, and I have my second output block. Next, I'm going to bring in the second block from run 1, second block from run 2. So I have 6, 7, and 3, 5. I'm going to look at the heads of those 2 lists. It looks like 3 is smaller, so I'm going to process 3, put it in the output. Now I'm going to look at 5 and 6. 5 is smaller, so I'm going to put it in the output. Go ahead and output 3, 5. Here I'm going through an overly detailed explanation of a merge sort. Essentially, what I'm doing is I've sorted 2 components, 2 sequences of blocks, stored it in disk, and then doing a merge sort of those runs. In this case, I have only 2 runs. In many cases, I might have more than 2 runs, in which case I'm looking at the heads of all of those lists and then merging them and populating the output and throwing the output out. Is this clear? This is simply merge sort. So I'm sure you've looked at merge sort in some course in the past. Right? Okay. All right. So this was the case where m is equal to 3, b of r is equal to 6. Let me go back to m is equal to 3 and b of r is equal to 9. Notice that if I wanted to do a merge when I have b of r is equal to 9, this was an example that I tried to do earlier but failed. If I have b of r is equal to 9, then I basically have 3 sorted runs. Okay, so you can think of that as 3 sorted runs that I want to merge and then output into an output buffer. Unfortunately, for doing so, I need to have 1 representative from each of those blocks in memory. Here, however, I have only 3 blocks in memory. I can only store 3 blocks in memory, but I need 4 blocks. I need 1 from each of those 3 runs plus 1 for the output. Okay, because of that, I can't sort a relation with 9 blocks using 2-pass multi-way merge sort because of these constraints. Okay, because I have a memory limitation, I can't actually do this. So the way I would have to do this is basically I would have to do multiple passes, right? So I would take m-1 sorted runs, merge them, write out another sorted run, take another collection of m-1 sorted runs, write out that collection, and keep doing this up until I've merged everything. So this is essentially like a recursive merge sort, if you will. Okay? But let's get back to why this b of r is equal to 9 did not work with a 2-pass multi-way merge sort. And I have some math for that. So So the steps for the 2-pass multi-way merge sort is you read m blocks at a time, you sort and write them out. As a result, you have runs of length m on disk. Then you merge m minus 1 runs at a time, construct the output, so output occupies 1 block, and then you write it out to disk. So at the end of step 2, you have runs of length m times m minus 1 is equal to roughly proportional to order of m square, because you have m minus 1 runs, each of which have m items. So you can basically sort up to order of m square items at a time. Another way to reason about the same thing is you need B of r divided by m. So if you chunk up the relation into collections of length m, then the number of such collections, the number of such runs has to be less than or equal to m minus 1, because you want one representative from each run to be in memory. In order to do that, B of r must be less than m times m minus 1. Approximately, B of r should be less than m square. Okay? So B of r needs to be less than m square in order for us to be able to do this 2-pass multi-way merge sort. However, in our example, m was 3, B of r was 9. So B of r is not less than m square, and therefore we weren't able to use 2-pass multi-way merge sort for our example. Okay, but on the other hand, when B of r was 6, then we were in good shape, right? So we were in good shape when B of r was 6, but when B of r was 9, we ran into issues. Any questions about this? Okay. So what is the cost of doing this? Let me go back to that for a second. The cost of doing this operation is 3 times B of r. Can anyone explain why it's 3 times B of r? Any guesses? So think about what is going on in each step, right? So step 1, you're reading your relation m blocks at a time, doing some operation on it, and then writing it out. Right? So essentially what you're ending up doing for step 1 is you're reading the entire relation once, and you're writing the entire relation once. Step 2 is going to read the entire relation once again, because you are taking all of these runs in and then writing the output. But remember, we are not counting the cost of writing the output. So you have a read and write for step 1, you have a read for step 2, therefore your cost is 3 times the number of blocks of relation R. Okay? All good? Okay. So the cost of table scan is B of R, the cost of sort scan is 3 times B of R if you're doing it in this way. And this is assuming B of R is less than m times m minus 1, less than or equal to m times m minus 1. The cost of an index scan is once again B of R. The cost of doing a sort scan, if you have an index on sorting key, is once again B of R. So this is much better than 3 times B of R, because you don't need to write out, read back in, and so on. So that's not necessary if you're doing an index scan. If you have an unclustered relation, I'll briefly discuss an unclustered relation for a second. Most of the lecture I won't talk about unclustered relations, but so far you've been assuming that the tuples of R are clustered, they are dense, they are stored in B blocks. But if the tuples are interspersed with other tuples of other relations, then in the worst case, the number of blocks is T of R, and therefore, in order to sort, applying this 2-pass multi-way merge sort would be T of R to read all of the stuff in once, and then after that, when you're writing it out, you can make it dense once again, right? So when you're writing it out and then you're reading it back in, you can make it dense, and therefore the second time and the third time around, it is 2 times B of R, but the first time it's going to be T of R. Okay? So once again, the first time when you're reading it, it's since the data is spread out, the cost of reading all of those blocks is T of R. Once you've brought it in, you can make it dense, you can write it out. That makes it B of R to write it out, and then B of R to read it back in, and therefore the second and third components are B of R. The first component is T of R. Okay? All right. So let's move to other operators beyond scan. These other operators are fairly more complicated than scan, and so it's important to think about another way of classifying these operators and also see how it fits in with the rest of the plan. So one thing for us to think about is how these operators are actually implemented. For scan it was less important, but for the other operators it's more important. The way these operators are implemented is via an iterator model. So each operator is implemented using 3 functions. The first function in some sense sets up the operator or sets up the operation. It sets up the data structures and performs certain initializations. The next operation returns the next tuple of the result. And the third operation is close this NZ operations and cleans up the data structures. So if you have these 3 operators, 1, 2, and 3, 1, when it sets up, when it starts, you would run open on this operator, which will set up the data structures, and then you would call get next from this operator. From the calling function will call get next, and 1 will be responsible for fetching each new tuple and then sending it to the operator higher up in the plan. And then when it's done, it will call the calling function will call close when you're done, and then that'll be responsible for closing up the execution of that operator. 1 in turn will use get next of 2 to get data that is necessary for its processing. So one example of this might be, let's say this is an operator corresponding to selection. The selection operator might ask the operator below in the plan to give me the next tuple so that I can apply the selection condition on it, then pass it to the tuple above. Okay, so maybe operator in 2 is a projection, maybe operator in 3 was a scan. So you might have a scan followed by a projection followed by a selection. So the scan is generating tuples, passing it to the operator above. Operator above number 2 is taking those tuples, stripping away all the fields that are not necessary, passing it to the operator on top, which is the selection. The selection condition is filtering out the tuples that don't match, passing it to the operator above, which might be the output. So that's one way of visualizing and thinking about the implementations. So you can think about each operator as operating in this iterative model or in the iterator model, where they iteratively work on tuples one at a time and then pass the tuples to the higher level operator or the calling operator that is calling for the next output tuple. So one benefit of this iterator model is that it enables pipelining. So you don't need to wait for any of the operators below to finish execution before you get your first operator. So as I'm scanning at the bottom operator, any tuples that I find I can send to the next operator pi, which is projection, and those tuples can be sent to selection even though scan might not have actually finished. Scan might have not even finished its processing, but those tuples can move up to the higher levels of the query plan. So another alternative is to wait, right? Another alternative is to say, okay, I'll wait until I've scanned everything, and then after I've scanned, then and then only will I apply projection, then and then only will I apply selection, right? That, of course, has a downside that you have to wait until each operator is completed before you start execution of the next operator. The benefit of this iterator model is that it allows you to pipeline the operators such that you can operate on many tuples in sync across the plan. So these tuples will flow through the plan to the higher operators in the plan and then go to the output. Okay? So this allows us to have many operators that are active simultaneously. Again, we are not going to be able to get into the details of how to implement these operators and how these functions look like for each operator, but this is just to give you a sense for how these operators fit into a query plan. So there are obviously cases where pipelining may not be possible. So if, for instance, you're doing a sort scan, then it might be very hard for you to throw up one tuple at a time as you're sorting it, because you have to wait until the sorting is complete. Okay, so there are cases where you're blocked, you are artificially blocked between two operators because you have to wait until the results of one operator is finished before you can send it to the other. So sort scan is one such blocking operator. Another such blocking operator is group by. Group by, once again, you can't really simply send up tuples to the next operator. You have to wait until the group by result is computed before you can apply the next operation on it. It is not meaningful to send partial results for group by, but for scan, for selection, for projection, all of these types of operators, it's perfectly reasonable to send up one tuple at a time. These are non-blocking operators. Okay, so group by, sorting based operators, these are blocking. And even within some other operators, so joins, for instance, there are some operators that are blocking, some implementations that are blocking, some implementations that are non-blocking, and we'll get into that in a little bit. So the first overview of general operator implementation, so the first classification for it is based on whether you use a sorting based method, a hash based method, or an index based method. And I'll get into what each of these mean in a little bit. The other classification is based on number of passes. The first classification here is one pass. So you read the data only once from disk. So for this to work, at least one of the arguments must fit in memory, and I'll tell you why. The two-pass alternative is when the data need not fit in memory but is not too large. Remember, even for sort scan, we had this constraint that B of R is less than or equal to M times M minus 1. This is not a very hard constraint because the B of R in many cases is smaller than M times M minus 1. But so basically this says that the relation R is not too large. The multi-pass categorization basically has no limit on data size. You can have data as large as you want. Okay, so these are the two classifications, hash index sort, or one pass, two pass, or many pass. Another classification you can think of is blocking versus non-blocking. This we will not focus on as much, but I just wanted to mention that because we covered it in the iterator intuition. There are two metrics that we are going to be caring about. Again, this is the same things that we worried about for the sort scan implementation. The first metric is the I/O cost, right? The amount of all the I/Os that are necessary up until the point you are ready to write the result to disk. The second metric is a buffer requirement, which is how large should M be in order for you to be able to apply the operations that you need. So we saw examples of this for sort scan, so that's good. Maybe I should stop now, given that we just have 5 minutes. I'll tell you about the 1-pass, 2-pass, 3-pass, and index-based implementations on Monday. Any questions about this stuff so far? Okay, all right, I'll see you on Monday.